Hi, I'm Steve Sobek, and the purpose of this video is to mathematically prove one of those many tricks, mental math tricks, that I teach you from the homepage of my website, amysflashcards.com. This particular trick is the trick that applies when we're multiplying two numbers that fall within the range of 11 to 19, like 13 times 15. Both of these numbers are in that range. We're not supposed to memorize the answer, but when we use the trick properly, we should be thinking in our head, what is 180 plus 15? Well, that would be 195. That's the final answer. Let me type that in. We're thinking 180 plus 15, and that brings us to our final answer of 195. All right, now, how did we get the 180? Well, according to the trick, okay, and then again, those tricks are all articulated in those special links next to my drills on the homepage, special strategies, tricks. All right, but here it is, in case you skipped that part. The trick is to take this 5 and add it to the 13. All right, well, that's 18. So let me just write this down. We take the 13 plus 5, okay, which is 18, and we take that result and add a 0 to the end of it, which is tantamount to multiplying it by 10. So we're multiplying that by 10. So that's 18 times 10, 180, plus we multiply these two single digits together. We multiply the 3 times the 5. That's how we get the 15. And 180 plus 15 is 195. So we can calculate the answer using the trick. We can calculate it mentally without any paper or pencil pretty rapidly. All right. Now some of you might be wondering, why does that trick work? Or does it work all the time? It worked in this particular case, but is it reliable? I'd like to see a mathematical proof of that. All right, so that's what the purpose of this video is to mathematically prove this mental math trick. Now I'm going to prove it for numbers in the range of 10 to 19, although we only use it in real application for numbers between 11 and 19, but it works for 10 as well. But we have a special trick for multiplying by 10. We move the decimal point to the right one place, which is a much better trick. All right, but it works here too. So on this the next slide here, we are going to do the mathematical proof. All right, I'm going to define my variables. We're going to let x represent any single digit number. In other words, numbers like 0, 1, 2, 3, 4, 5, all the way up through 9. Likewise, y will represent a single digit number, 0 through 9. Consequently, the expression 10 plus x represents a number within our range, 10 to 19. And likewise, 10 plus y represents a second number somewhere within the range of 10 to 19. All right, what I need to show, and I'm going to type this because my handwriting isn't all that neat. We're trying to show that if we take one of these numbers, 10 plus x, and multiply it by another number within that range, 10 plus y, we're trying to show that the result of that is going to be equal to, let me move this over here, is going to be equal to, okay, now what is the trick? The trick is we take the first number, 10 plus x, and we add to that the single digit from the second number. We add to that y. Then we take the result of that. All right, let me put this all in parentheses. Go back here and put another parentheses. And we add a 0 to that. All right, so when we took the 13 plus 5 is 18, then we multiplied it by 10, or added a 0 to get 180. So we're going to multiply this by 10. And then we take the result of all this and add to that the product of those two single-digit numbers, x times y. That's what I'm trying to demonstrate. I'd like to prove that this left expression is equal to the right expression. All right, so we're going to take the left expression and we're going to manipulate this through legitimate transformations until it looks like this right expression. And when we have achieved that, we have concluded the proof. All right. Now, we're going to multiply these two binomials together. And, of course, through multiple applications of the distributive property, we know that we're going to take each term on the left side and multiply it by each term on the right side. Some people think of that as FOIL, firsts, outsides, inside terms, last terms. Those are the lines of multiplication when we multiply two binomials together. We're going to take the 10 times 10, that gives us 100, plus the 10 times y, that would be 10y, plus we'll take the x times 10. Of course, multiplication is commutative, so x times 10 is equivalent to 10 times x. So I'm going to write 10x plus the x times y. Okay, well notice that this expression ends with a plus xy, and we desire the final result to end with a plus x plus y. Well, that's good. So this part right here, this part of the expression, we are not going to tamper with that. That is the way we want it to end up. But the rest of this expression, we're going to take this and continue to manipulate until it looks like this. All right. All right. We notice that from these three terms, we have a common factor of 10. All right. Well, then let's factor out that common factor of 10. 10 times the quantity. See, 10 times 10 would give us 100. Okay. We'll need a 10 times, we need a y here to get the 10y. And 10 times x would give us the 10x. And we still got the plus xy, which we're going to leave alone. Now within the parentheses, we have a y plus x. We know that addition is commutative, just like multiplication was, as I applied up here. So commutative means we could change the order of the addition without changing the value of the expression. Y plus x is equivalent to x plus y. So let's change that. Let's make this 10 times the quantity, 10 plus x plus y, and we still got that plus xy sitting out here. Now, addition is not only commutative, addition is associative. The associative property of addition tells us that we can change the groupings. If we have a bunch of addition, we can group it any way we want without changing the value of the expression. So we're going to take these first two terms and group them together, put parentheses around them. That won't change the value of the expression. This will be equivalent to what it was. All right, so now we're going to have 10 times the quantity of 10 plus x, plus y, and we still have the plus xy out here. Okay, now look what we have now. This expression right here is now equivalent to the expression that we had desired, which means the proof is over. We have demonstrated that this original expression, the product of these two numbers that range between 10 and 19, is equivalent to this expression here. Okay, this expression is equal to this, and this is equal to this, and this is equal to this, and this is equal to this, which is the right expression. By the transitive property of equality, the original expression is equal to this final expression. So the trick is valid. It will always work. You can have confidence in it. Now you might be asking, do I need to understand the proof of this mental math trick in order to use it properly? Absolutely not. Does understanding the derivation of this procedure facilitate its memorization? No, that is sometimes the case. Sometimes it does help you remember a theorem when you see its derivation. Not here. I don't think so. Now, what good is it? Well, your curiosity has been satisfied, and if someone were to ask you, why does that work? Or is that valid? Will it always work? You could say, yes, it is valid, and here's why, and you can show them this proof. Hope you enjoyed that. That concludes this video.